Hello, welcome to Dr. Taylor's demo lesson. Today what we're going to talk about is multiplying decimals. Now I know you all know the algorithm, all right? You all know the algorithm, and that's great, and we want our kids to know the algorithm eventually, right? The thing I like to say is the learning sentence. The learning sentence, the period is the algorithm, the capital T is not. I don't start with an algorithm, I end with it. And if I'm really fortunate, I get the students to give me the algorithmic understanding through the pattern recognition they discover through an analyzing process. Okay? So what I'm going to do is I'm going to build the capacity for a student who's struggling with a number of things, all the way up to getting a sense of what that multiplication of decimals entails, thinking and concept-wise, build it toward an algorithmic activity. So, I will start with a problem, and I'm going to use, let's see, yeah, I'll use that one. 27 times 13. Okay? There are no decimals in that. Well, there are, obviously, but the decimal is at the end of the whole numbers, 27.0, 13.0, but no one's thinking about that initially. No student is, right? So what we have to do is we have to build that understanding up. Now, to do this math, some of you will go, oh, 3 times 7 is 21, carry the 2. I don't want to do that algorithm either. I don't want to do any algorithms, all right? I want to build it up completely from the get-go, all right? So let's start out with saying, okay, understanding this. What is this place value on the 13, all right? What is this place value on the 1, etc.? And getting them to understand their place value system. The 1 space, the 10 space, the 100 space, etc. Using grouping and adding zeros to multiply by 10 and all those elementary strategies that you can unfold in the course of this lesson, right, can be utilized. So I'm going to do the Common Core procedure, or the, well, Common Core is really a methodology, or it's not a methodology, but it's a set of outcomes, right? So the strategies I'm going to use support Common Core outcomes, let's say it that way. So what place is this? This place, that's the 1's place, right? Right, students, yes? Okay, so when I multiply this number times that number, is that really a 2? That's my question. Is that a 2? Do you think so? Some of you think not, right? Okay, so agree with me if it's a 2. Okay, I've got a lot of agreement, some people not. Well, let's think about this. What is that? Is that a 7? If the decimal were here, 7 1's, but is that 2 more 1's? Is that 7 plus 2? Is that 9? No, it's not 9, is it? What do you think it is? You think it's times? Well, is it 7 times 2? Is it 14? No, no. But it's a place value, right? That's 7 1's and 2 10's, right? So that's 20, isn't it? So now with that understanding, we can do the mathematics without the algorithm. 3 times 20 is what? Well, 3 20's, I could do that as 20 plus 20 plus 20, right? Can I think about multiplication as multiple additions? Absolutely. Is that going to get the job done? Absolutely. Is there any intrinsic value except for speed to memorizing multiplication tables? Not really. And when we have a phone and a calculator, we don't have to. But we do need to understand the structure of place value. So what is 20 and 20 and 20, or 20 3 times, right? 20 is appearing 3 times, right? So that's 3 times 20, or that is 60. Now, we've done that 20. Let's do that 7. What's 3 7's? Again, that's 7 and 7 and 7, right? And 7 and 7 is 14, and 7 more is 21. So now we've multiplied that 27 by 3. But we also need to multiply it by this 1 here. But is that truly a 1? What did we learn? Exactly. We learned that that was a 10. So we're multiplying this 27 now not by 1, but by what? That's right, by 10. So what is 10 7's, right? Or 7 10's. It doesn't matter which way you think about it, right? But if I do 10, 20, 30, 40, 50, 60, 70, so 10 sevens is 70. Now is this 10 twos? No, that's 10 20s. So that's 20 plus 20 plus 20, 10 times, right? And I would really, it's best if I stick that all the way out, okay? Show the entirety. So what is 20 10 times? Well, we know when I multiply by 10, it's really doing what? There's a little trick. Now, it's an algorithm, but you can do it longhand. But when you realize the pattern, you realize when I multiply by 10, that's right, I simply add a 0 at the end. So 20 times 10 is 20 with a 0 at the end. What is that? That's right, it's 200. Okay? So now look, I've had 4 numbers, and I multiplied all 4 pieces, and I've got 4 products. Do you see the connection to distributive property that's being done here? This is algebraic thinking. This is why it's important not to just teach an algorithm. They learn to group products and then combine like terms. All those things we want them to know in algebra, we want to teach them, are predicated on this elementary understanding. All right, so let's do this. This is 1, 7, 8, 9, 9 and 6 is 15, right? So now if I said 15, right, I still have to add those together, don't I? And what is 2 plus 1? It is 3. So 351 is our answer if I'm multiplying, okay? So what I'm going to do is I'm going to go ahead and say carry the 1 so that I don't have this extra line here that might be confusing to some kids, okay? So that's 200, carry the 1 is 351, if I'm not mistaken. 7 and 9, 9 and 5. 9's almost 10, 10's 1 more than 9, so 5 is 1 less than 6, right? If I take one of these 1s and put it with those, I get 10 and 5, which is 15. Then mental grouping. Explore that, challenge them, ask them to think about it, ask them to come up with creative ways to do these things. Spend that time in your room developing those skills, and that will save you all that time the rest of the year. You can get all of these skills wrapped up in the first few weeks to a month. If you do this regularly, all the time, often, those kids who had that missing piece, they will gain that understanding. All right. So now I said I was going to multiply decimals, but all I did really there was multiply whole numbers, right? That's really all I did. And we discovered that when multiplying, I can think of it as multiple additions or repeated addition. When I'm multiplying, I could transfer ones or whatever. What we probably should have done, and I think what I would have started with, is an estimation. Okay? Estimate. What this number 27 times 13 would be. And this is not just a guess, right? This is them thinking about how they could organize it or how they could make those numbers more friendly to do mental mathematics. That's what estimation is. Mental mathematics with friendly numbers that I can then get my head around them easily. So if I look at 27, I could estimate 27 to be around 30. I could have said around 25. I like zeros. Zeros are round and they make the numbers easy. Notice that I added 3, right? And I'm thinking about that. I added 3 to get 30. Okay? Well, I will also then would like to multiply that by a number that is rounder than rounding 13 up to 20. That wouldn't be a very good estimation. But I noticed that if I subtracted 3, what would that be? That's right. That's right. That would be a 10. Okay? And 3 times 10 is approximately equal to 300. Now, we know now that our answer is 351. But it gives us the ballpark range, right? It gives us the ballpark range. And by doing that, we can estimate the, what's the word I'm trying to think of? Not legitimacy, but reasonability of that number. It's reasonable that that's the answer because it's 300 something, right? And even though it seems like I added 3 and took away 3, it should give me an exact thing, but we see it doesn't. So when you break in those numbers apart to do multiplications with broken values of addition, there is strategy to that needs to be developed. Okay? But right now we're going to save that for another lesson. Save that for an actual multiplication strategy lesson. So I just dropped my pen. So what I have here is a situation where I've uncovered how to multiply without algorithm. I've talked about how to add and how to multiply with repeated addition, and I added in a column. I could have added a lot of ways. Adding up all the ones gives me a 1. Adding up all the tens gives me 15 tens. Well, 15 tens, if I write the 15 over here, then the 2 hundreds and the 100s, because 15 tens is 5 tens and 10 tens. What's 10 tens? It's that 100, and that's what carrying's about. I'm saying that's a 15, not 15, but 10 tens and 5 tens. Very important. Those are the fundamental understandings that stop kids from getting this reasonability part down. All right? So now, we're going to continue. Let's add something to it. Let's add a decimal. All right? Let's explore what a decimal might do. What if I put a decimal right here? Okay? Can you see that? If I put a decimal right there, so that's no longer 27, is it? What is it now? That's right, it's 2.7. Now, I like 2.7, and that's clearly what it is. And if you wanted to express the numerical things that are on the board to me accurately, 2.7 is wonderful. But if you wanted to express the actual value of that numeral, not just its symbolic reality, right? It's 2 and. That's what that decimal means, and. Why? Because now it's a mixed number. It's 2 whole parts and 7 fractional parts, isn't it? Because after the decimal, it's 1, 10, 100, but after the decimal, on the right side of it, it's 1, what? So if I went, here's my decimal, here's my ones place, and what's next is my tens place, and what's next is my hundreds place, right? So if that's the case, 1, 10, 100, going backwards, some of you might want to say negative 10. Now actually, it's not negative 10, but that notion of being negative to the left and to the right and positive to the left, that's an important notion when we think about powers of 10, and we'll talk about that later. It's really what the number system's based on. But this is not negative, it's 1/10. And so 1/10, what do you think the next one would be? Using that as a clue, that's right, 1/100, right? And so that just keeps going in both directions. So I just thought that was important to say, look, here's my decimal point right there, all right? And that decimal point is meaningful. And it means and. It's like 2 and 1/2, right? The 2 part is the whole part, and the 1/2 part is the fractional part. That decimal means and. Never use the word and in a number. Like if you got 3,253. People tend to put an and on that comment, 3,200, or 3,253. None of that's true. The word and, when you're talking about the name of a number, the word and is where the decimal point is. And why do they call it a decimal point? Well, all of these numbers, 10, 100, 1,000, 10,000, those are powers of, or multiples of what? 10 times what is 10? 10 times 1, right? Good. 10 times what is 10? Right. 10 times 2. 10 times what would be 1,000? 10 times 3, right? So these are all 10 times 10 times 10, and here I'm dividing by 10, dividing by 10 times 10, dividing by 10 times 10 times 10, right? That's really what it's about. That's what it's about. And since 10, think about what is a decade. How many years is a decade, right? How many in an Olympic decathlon? How many events do they compete in a decathlon, right? That decade, decathlon, decimal, that DEC prefix, not really the prefix, root is a better word for it. That DEC root means 10. This is the base 10 system, right? That's why it's called a decimal point. There's no decimal points in a binary system because a binary is based on 2. All right? And that's a whole other thing. But the notion is, because it's called a decimal point, it's representing base 10s, and they're all 10 to a power. So now let's look at this. If that decimal point lives there, this is 2 and 7 what? 7, very good, 7/10. So what that means is that's now estimating it. It's not almost 30 anymore. What is it almost? 2.7, 2 and 7/10. It's almost 3, yeah? Okay, so let's look at this multiplication. Well, when I multiply 3 times 20, I got 60, yeah? When I multiply 3 times 2, what do I get? Yeah. What do I get? 6. Very good. So instead of 60, I wanted to get 6. How can I write that number differently so that it looks like a 6 and not a 60? Can I just erase the 0? Well, I could, but then that would put the 6 in the tens place, right? Because this is ones, tens, hundreds. But if I put my decimal next to 6, now it's 6.0. Now, of course, that means it's out of alignment with these, but let's see what happens just to watch for patterns. See what patterns you see. So now if I did 3 times 2 and some change, I got 6, right? But what about 3 times the change? What is 3 times 7? When we did that, it was 21, remember? But now, is that a 7? No, that's a 0.7. That's a 7/10. So when I multiply 7/10, which is less than 1, by 3, what's 3 times 1? Very good, it's 3. So I'm multiplying 3 times a number less than 1. Obviously, my answer is going to be less than 3 times 1, or 3, right? So I'm coming down here. 3 times 7 was 21, but 3 times 0.7 is going to be something less than 3. What's less than 3? What can I do to make this less than 3? I think you figured it out. You're astute. You're smart. You see it. Okay? So now let's continue. Let's continue and look at this. So what is 1 times something less than 1? What's 1 times 1? It's 1. So 1 times something less than 1 is going to be something less than 1. Well, here we did 1 times 7, right? Or, I'm sorry, that's not a 1, is it? Oh, you got to catch me on these. You can't just let me run wild with that. What is that really? That's not a 1. What is it? That's right, it's a 10. It's in the 10. That's a 1's place. That's 3 1s and 1 10. 10 times 7 was 70. So 10 times something less than 7, right? Something less than 1, I should say. So 10 times a fraction of 1 is going to be less than 10. Because 10 times 1 is 10. 10 times a half is half of 10, right? 10 times 7/10 is 7/10 of 10. So what happens here again? When I multiplied this times that was no longer in the 1's place. It moved over 1 decimal place. So I'll show where that decimal place is. 10 times 0.7 is 7. And you can check that on your calculator. Okay? Verify it. Is 10 times 0.77? Yeah. And then what's the way to think about how that happened? How did I make that? Couldn't I have thought about that in an easy way? When I'm multiplying by 10, what happens to my decimal? Right? Think about when you convert percents to decimals, you learned a little strategy. When I'm multiplying by 10, my decimal is basically moving. And it's moving to make the number bigger. 7 times 10 becomes 70. Times 10 becomes 700. Times 10 becomes 7,000. So that decimal is moving, and it moves 1 place for every 0 on that number, 1, 0, 0, 0, 0, that I'm multiplying by. So how many zeros were on a 10? 1. And how many decimal places did it move? It moved 1. Does that make sense? Yes? Yes? At this point, I would have them explain their understandings, and at a few points I would have had them do that. I will do it in front of a regular class, and you can watch it happen in real time. But this is a little bit of something to be a tutorial for teachers to help them pull together all these skills that they didn't necessarily have because they weren't elementary school teachers. Okay? And finally, let's take a look at what's 10 times 20, but this is no longer 20 because that decimal, what did that become? It became a 2, so 10 times 2 is what? A 2 with a 0 behind it is 20. Good. How can I turn a 200 into a 20? I put my decimal places. So now, these are all in the ones place, and these are all in the tens place. So what are these all in? They're in the tenths place, right? Well, it's then no longer 351, is it? When I add up 0 and 0 and 0 and 1/10, I have 1/10. So I need that decimal. Check that out. You notice that? You see something? Is there anything you're noticing that might be helpful when you add up these numbers? Because remember, these numbers get added, right? 9 and 6 is 15, 5 ones and 1 10, 10 and 20 is 30, that's 35. And 1/10. You could say 35.1, but 35 and 1/10, it's just better. It's just more, there's more knowledge in that statement that you're offering me as the listener. I need that knowledge if I want to understand what you're saying, because you're explaining to me your solutions. Okay? Better than that, you're explaining them to one another. That's really the goal. Okay. So, well, what would happen? Let me just erase these things here. All right? What would happen if I not only had a decimal here, but I also had a decimal there? 2 decimals. And I could have those decimals in any place, right? I just put them in the middle to make it easy to look at it. Okay? But notice what I see. Let's start again. What is? This was 10. I'm sorry. This was 3 times 20, which was 60. Now it's 0.3, which is less than 1. And this is only 2. So 2 times a number less than 1 basically means I'm getting something less than 2. Right? 2 times a half. Let's think about what that means. Let's go 2 times a quarter. A quarter is even less than 1. And what's a quarter as a decimal? Everybody knows how many pennies it is, 25 cents. So a quarter as a decimal is what? $0, point, and 25 cents. So 0.25. What's 2 of those? What's 0.25 and 0.25? What's 2 quarters together add up to? That's right, 50 cents. So that's 0.5. So when I did 2, which is a whole number, times 1/4, which was a little number, I converted it to decimal to make it think about money, I got 1/2. 2 quarters is a half a dollar. So you see how multiplying a number by a small number that's less than 1, that's important, not just any small number, a number smaller than 1, a number by a fraction, I end up with a smaller number as the product than my original number was. Because when I multiply it by a fraction, I'm basically cutting it into pieces and then taking multiple pieces and lumping them together and seeing how much there is. So what is 2 times 3/10? Okay, that's a good question. What is 2 times 3? That's 6. So it's going to be 2 times 0.3 is going to be less than 2 times 3, right? And 2 times 3 was 6. What we put that decimal there? But 2 times 0.3 is less than 6. So guess where that decimal goes? It goes over there, right? Because this is a small fraction, doubled. I'm even less than 1, aren't I? Because 0.6 is kind of 60%, right? Right? You're thinking about your test scores and all that silly stuff, right? But that's important, just not necessarily as an end-all, right? But I do want to be able to convert and think about them in a way that makes sense to me, and people understand getting a 60% on something, okay? So that was the first multiplication. Now it's 0.3 times 0.7. Well, what happens when I take a little number smaller than 1 and multiply it by another little number smaller than 1? Well, what happened when I took a whole number and multiplied it by a number smaller than 1? What was my product? Right? Was it more than this number or less than that whole number? Right, it was less than that whole number. So if I take a small number, even though it's less than 1, and multiply it again by a number less than 1, guess what? I'm going to get an even smaller number, right? It doesn't matter that it started out less than 1. When I multiply it by a number less than 1, it's going to get smaller. It's kind of like dividing, but I don't want to talk about that. So when I multiply 0.3, which is less than 1, times 0.7, which is less than 1, I'm going to get a number that's less than 1, definitely, and less than 0.7. So, well, we know that 3 times 7 was our 21, and we had a 0.7, that gave us 2.1. So when we had a 0.3 times a 0.7, that's going to give us a 0.21. Is that less than 1? Absolutely. 2.1 wouldn't have been, would it? But it's also less than 0.7, isn't it? Less than that original number. Now it's less than 0.3 as well. I don't know if that's a pattern that continues, but that's something for you to look at, something to check out. Students, help me. So let's move on. We did 0.3 times those. Now we're going to do 1. Well, what's 1 times anything? It's itself, isn't it? We can do that. What's 1 times 2 going to be? It's going to be 2, right? Not 200, so 2.00. What's 1 times 0.7 going to be? It's going to be 0.7, not 70, 0.7. So now look what happens, right? That 1 was still carried. I'm going to put that in red. Because I still have 9 plus 6, which is the same thing as 10 plus 5, which is 15. 5 of those and 1 of the next column. So what happens now? What is 2 and a bunch of little bits of change? Is it going to add up to 351? Is it even going to add up? If I had $2 and 3 piles of change that were less than $1, will it add up to $35.10? No. Will it add up to 35 cents? No. Because what's 2 and a little bit of change? It's going to add up to something a little bit more than 2, like 3.5. Do you notice anything now? Is there something that you notice? Are you seeing a pattern? I bet you are. Are you noticing that when I add, and I'm going to say combine because it's a better word than add, when I combine all these numbers together, if I slid all that change into one pile and counted it, that's how much money I'd have, right? That's combining. When I combine them, notice how the decimals lined up. And of course they will, because when I add up the ones places, then I add up the tens places, then I add up the hundreds places. Well, then basically the decimals were always aligned on the end. I just never looked at them. But now that the decimals have moved, right, I'm adding up all the ones and all the tenths and all the hundredths. I'm combining like terms in this case. Hundredths go with hundredths, go with hundredths. Tenths go with tenths, go with tenths. Whole numbers go with whole numbers. Tens goes with tens. Hundreds goes with hundreds. And I need that decimal location to tell me what that is. Check that on your calculator. See what you think. And I'm going to offer you a challenge problem. Tell me, what is 0.27 times 0.13 going to be? Okay? What I'm going to do now is I'm going to ask you to work together. I'm going to ask you to not use your calculator. I'm going to ask you to use this expansion and try to modify it or create your own, really. Don't just copy it. But then modify it to represent what those decimal numbers would be. And then I'm going to ask you to explain your understanding. I'm going to ask you to tell me how you did it. I'm going to ask others of you to explain that. I'm going to ask for agreement. I'm going to ask, was there a different way? And there's going to be. All right. Some people are going to do it in a different order. Is that going to be okay? Absolutely. What are you showing there? You're showing that addition can be done in any order, right? So you're showing those algebraic properties again. All of the algebra skills you want them to understand when you present algebraic concepts to them are embedded in the fundamental understandings that they get from elementary school mathematics. This grouping, this place value, this stuff, and this is what you've got to do. And even if you're the algebra teacher, this is what you've got to do. Use it as a do now. Use it as an exit ticket. Use it as a free time game for points with teams. There's a lot of ways you can use this stuff, right? And when you use it, you drive home the understandings so a kid knows what they know. And they know why their answer is legitimate or not. And they can take a criticism of their answer because their explanation allows them to hear an explanation. The more I speak an explanation, the more I can hear an explanation better. And when you're wondering why you can't just tell them knowledge, if they can't speak an explanation of their thinking, how can they accept your knowledge? Because they don't know how to think and express it yet. It sounds harsh to say they don't know how to think, but they don't know how to think. Now, they do know how to think. Of course, they think about a lot of things, but they don't know how to think in school because we beat it out of them. Give me an answer. Give it to me quickly. Now let's move on. Just do this. Keep change flip. That's all. Just remember that. Just remember that this day. 2 days later. Just remember that. 3 days later. Just remember this. 10 days later. Just remember that and that. Pretty soon, at the end of the year, they've got about 85 just remember thises, and you wonder why they don't remember them. Of course they don't remember them. They're not going to remember them. And they're meaningless memories if they do remember them. They won't know when to apply it and why. Driving through this as your beginning point to get you to letting the students say, well, look, they all line up. And then, you know what? There was 2 decimal places, and it was over 2. There was 1 decimal place, so there's 4 decimal places. What might that mean? This is the way you develop an algorithmic understanding. Okay? And it's not to say what you do is wrong or improper. It's to say what you do is insufficient to the needs of the students in your classroom. And if we want to meet their needs with sufficiency, we have to bring a part of what they should have had in elementary school up. But it's not 2 weeks of drilling how to do multiplication algorithm, how to memorize multiplication facts. It's learning how to use this kind of thinking process, how to use this kind of grouping process, and how to build an understanding and a fluency to explain their understanding so that when they get a calculator answer, they go, wait a second, 2.5 times 6.3, that can't be 375. There's got to be something wrong. They might not even know what's wrong, but they know enough to punch it in again and see, and they realize, oh, their little finger missed the decimal point in the first one, even though they thought they hit it. This is what you want. And those thinking students, you'll be able to corral them into group activities and problem-based learning. Okay? So let me close with saying thank you, and I hope that this gives you some strategies to use with your students to bring them up to where you need them to be so you can push them forward to their highest potential. Thank you very much.